El tema es Artificial Intelligence Applications for Subsurface. Inteligencia artificial, aplicaciones para subsuelo, con el doctor Deepak Davengoura de la Universidad de Oklahoma. Él es un profesor a tiempo completo de la Universidad de Oklahoma y con intereses en su investigación acerca de reservorios no convencionales, modelamiento y métodos de recuperación terciaria, así como aplicaciones de subsuelo en lo que es Machine Learning. Él tiene un máster y PhD de la Universidad de Texas A&M. Entonces, un conocido muy probablemente del doctor Marcelo Laprea. Él es profesor, el doctor Deepak es profesor y jefe en la Facultad de Ingeniería de Petróleo de la Universidad de Oklahoma, y le damos pues la bienvenida. Dr. Deepak, welcome to our session. Please apologize our delay, but we enjoy a lot, and I'm sure you recognize Dr. Laprea as well. Please go ahead with your presentation. Thanks.
Thank you, Dr. Armakanchi. Good to see some familiar names. Victor Huerta, good morning. And Dr. Luz Isaguirre, good morning as well. I'll go ahead and share my screen. Okay, so all of you can see this, I hope.
Yeah, Dr. Deepak, just give me a few seconds to clarify the audience.
Sure.
Señores, en el interés del tiempo y de reflejar lo más fidedignamente posible el mensaje, como mencionamos, haremos el esfuerzo con la facultad para tratar de editar esto en español, y más bien sus preguntas pueden formularlas en español, trataré de pasarlas en inglés, pero queremos avanzar con los diferentes ponentes que tenemos durante el día, y vamos a tener esta sesión en inglés. So I just wanted to mention that we will carry out in English, and when the questions comes, I will try to translate. But we are going to edit that in Spanish and distribute later on the slides. Thanks. Go ahead.
Fantastic. Thank you. Well, good morning, everyone. Thank you very much for the opportunity to present at this conference. I have very fond memories of Lima, and specifically of UNI. I visited Peru twice in the past, and had the opportunity to speak with several of the faculty members and meet several of the students down there. So thank you very much for this opportunity. So in today's presentation, I will be showing you a few things related to subsurface applications of machine learning. And over here, this work would not have been possible without the support of a whole bunch of people who work behind the scenes, mostly graduate students, as well as a few other colleagues and people from the industry. So I definitely want to acknowledge their contributions to this presentation. So anyway, so when we talk about machine learning, it's just become this huge buzzword. And over the last 10 years, we've been hearing more and more about that. And then we wonder why. Why has this suddenly become such a big buzzword? Well, it turns out that there's been democratization of computational power. There's also democratization of access to the internet. This is a very, very recent picture from about internet use worldwide. Close to about 8 billion people, and about 5.5 billion people are mobile users, and about 5 billion people are connected to the internet, and that's fantastic. Coming back to the previous speaker's point, I mean, the growth in the internet, it's been exponential, so it's just amazing. And you can see that close to about 4.5 billion people are social media users who use Facebook and Instagram and TikTok and all those other things. So it's fascinating that these 4.48 billion people on average spend about 2.5 hours per day. That's amazing. So every single day, there are 10 billion hours that people are spending on the internet. And what are they doing? They're posting pictures, they're liking something, they're posting things on social media. And each and every one of them becomes a data point. It becomes each and every one of those interactions with social media becomes a data point. These are all free services. And essentially that data is collected and synthesized to create information to help companies offer better services to you, and in some cases also lead to invasion of privacy, of course. But there are the more benefits to the use of these technologies than there are disadvantages if we are careful. But this is just an amazing story over here that 10 years ago, hardly anybody had mobile phones that were connected to the internet. And right now we're looking at this huge explosion in connectivity. And in case you don't believe me, this is what happens as of 2020. Every single minute, this is how many Google searches are performed. This is how many hours of Netflix people are watching. This is the number of text messages, 60 million text messages every 60 seconds. And if you just look across this whole thing over here, all of these are free services. They're free services because our interactions with them are creating data. So we are essentially creating all of this data, which is then being sold and synthesized and chopped up and diced for a variety of companies, typically to provide you with some services or to provide you with some purchase recommendations if you're talking about Amazon or any other online vendor. So that's what's happening in the internet space. And all of this has been made possible by huge advances in machine learning. We can actually synthesize all of this information and make recommendations to you. So if you talk about machine learning, what exactly is machine learning? So I'm just going to take a few steps back because I know that several of my colleagues and several of my students aren't exactly familiar with machine learning. So machine learning is really a very legacy term because the term machine was used to denote computers way back in the 50s and the 60s. And learning essentially just says something about using historical observations to predict or to make predictions for the future. And so I'm just going to take a quick detour into this website over here just to show you what machine learning is all about. It's really quite simple. So this is the website that I was pointing to on my PowerPoint slides. It's just a collection of pictures. So for instance, there's the world's largest collection of pictures. And over here, I hope all of you can see my screen. You can see different, pictures of different things. There are people who've drawn fans and cats and then camels and chairs and so on and so forth. So if I click on chair, you can see that across the internet, there are a whole bunch of people who've drawn pictures of chairs. And this is what it looks like. Close to about 200,000 pictures of chairs. People have drawn these chairs. And so they're out there on the internet. And so you can actually play a game which harnesses the power of machine learning, because what machine learning is essentially doing is it's learning historical patterns to predict something about some new data. So what I'm going to do is, over here, Google is asking me to draw a tiger. I'm going to fail because a tiger is pretty hard, but let me try. So I'm going to draw a face.
I see moon.
I can
or circle,
draw that,
or apple,
and then
or
blueberry,
mouth, or
eyes,
compass,
and then I'm going to draw the body,
or cat, or rhinoceros,
and then I'm going to draw stripes.
Or bear. Oh, I know, it's tiger.
So there you go. So based on what hundreds of thousands of people have drawn in the past, it was able to recognize that what I drew over there, even though it doesn't look like any tiger at all, a machine learning algorithm was able to recognize that that's a tiger. And here it's asking me to draw a kangaroo. Good, so let me go ahead and draw a kangaroo.
I see water slide. Or parrot. Oh, I know, it's kangaroo.
There you go. Just even without even drawing the entire picture, it was able to recognize that what I drew was a kangaroo. And likewise, I can draw a penguin
I
over
see
here.
line. Or nose. Or umbrella. Or backpack. Or short monster. I see popsicle. Or necklace. Oh, I know, it's penguin.
It was able to recognize it was a penguin. And then dumbbell.
I see line. Or garden hose. Oh, I know, it's dumbbell.
And then a nail.
Oh, I know, it's nail.
And then a fence. We're
I
almost
see
done with
line.
the game.
Or keyboard. Or square. Or jail. Or spreadsheet. Oh, I know, it's fence.
So there you go. So based on what I drew over here, it was able to recognize that this is a tiger, this is a kangaroo, a penguin, a fence, and so on and so forth. And you can just see how a machine learning algorithm was able to recognize my horrible, horrible drawing as a tiger. So I'm going to click on this, and this is what people have drawn in the past. There are hundreds of thousands of people who've drawn pictures of tigers, maybe some of your kids, maybe some of your colleagues, maybe you yourself. And a machine learning algorithm is looking at all of these pictures and then actually going up and then saying that, hey, this actually looks something like this down over here, but it could possibly also be an elephant. It could possibly also be a wristwatch. So you can see that machine learning can provide you with the correct answer, but there's also certain confidence levels associated with the prediction. It also thinks that it could have been an elephant or a wristwatch as well, but it got it right. So anyway, that's machine learning in a nutshell. It's essentially looking at past observations to make predictions for the future or to learn something about new data. And so when we talk about machine learning, typically in the oil and gas industry, we're talking about typically three forms of learning. There's supervised learning, where essentially you're modeling some input-output relationship. And specifically, it could be things like categorical output, where you have a bunch of inputs and you're trying to classify that data point as either being a spam email or not spam email, or whether it is a sand or a shale, or whether the pump is operating normally or the pump is headed towards failure. So these are all different kinds of labels. And when I say that every one of you has employed machine learning in the past, I'm not lying, because each and every one of you has also done regression. And that's a form of machine learning, where you're essentially trying to find a relationship between some input and some output. So that's a machine learning algorithm as well. So there's something called supervised learning, where you're trying to find input-output relationships. The output could be categorical or it could be continuous. And you also have something called unsupervised learning, where you're looking at patterns in data. And typically that's something like what Amazon might do, where they've collected a whole bunch of customer habits, and they want to group customers into different groups. A priori, they don't know how many groups are there. They don't know what the characteristics of the groups are, but you just want to group them into different categories or different clusters so that you can study their purchasing habits and make further recommendations. That's unsupervised learning. And there's something that's becoming more and more popular, which is reinforcement learning. We won't talk much about this because most of the applications that you would see are supervised and unsupervised learning. So just a few more minutes, if you bear with me, I'll just give you a few more fundamentals. As I mentioned before, you have some input and you have some output. And so you're going to learn a function that best approximates that relationship. And one of the forms of that relationship can be trying to fit a straight line through a bunch of points. Each and every one of you who's listening to this call, to this conversation, has done regression before. Each and every one of you has employed machine learning in the past. You have probably also employed classification as well, where perhaps you have two different classes and you essentially try to come up with some boundary that distinguishes between the two different classes. Maybe this might be spam, maybe this might be not spam, or maybe this might be sand, and this might be shale. And on the y-axis might be gamma ray, and on the x-axis might be neutron porosity. We do this all the time. So classification is also a problem. But really, what are we interested in? Why are we interested in doing these sorts of things? Because when we have all of our data and we learn from it, we can construct a model that looks like this, but that's not the end. The reason why we fit a straight line through a bunch of points or any kind of relationship is so that when I acquire new data, I can predict, use the model to predict some output variable. So this is a form of supervised learning in regression mode. If you're going to be talking about classification, then again, it's pretty much the same thing. You have some historical data, you're going to learn what separates out the different labels. So perhaps if you're looking at sand and shale sequences, maybe there's gamma ray on the y-axis, maybe there's neutron porosity on the x-axis, and this might be your shale, and this might be your sand over here. And so essentially you can construct a boundary between the two classes. But why would you want to do something like that? You would want to do something like that because if you get a new measurement from a new well, you want to be able to place that inside this space over here, this two-dimensional space, and then classify this point. And you want to do that in an automated fashion. Of course, petrophysicists and geologists do this all the time, so there's nothing new, but there's a mathematical framework to do something like this. And if you know that this one falls on the right of this dashed line, then it's going to be essentially a shale, and that's what you're going to be doing. So that's supervised learning. You can see that there's some output and there's some input variables or features, as we call them. And the output can either be a continuous variable or a set of labels. And then, of course, we have unsupervised learning. Unsupervised learning, you're just given a bunch of data, you're just given some characteristics or some measurements associated with those different data points. And if you want to view this as an example, let's just take this picture over here. I have 3 apples, and I have 2 bananas. And it's very easy for us to group them together. But how would you perhaps train, or how would you not train, but how would you get a machine learning algorithm to recognize that there are perhaps 2 different groups over here? Well, some of the measurements associated with apples are going to be maybe diameter, maybe aspect ratio, maybe vitamin C content. And so if you measure the vitamin C content and aspect ratio and things like that, and try to group these different data points into multiple groups, what you would end up with is you would end up with 2 groups over here, one of them that contains apples and another that contains bananas. So that's very, very straightforward. We can do this with extremely large data sets. And again, this is a very, very routine workflow for petrophysicists and geologists, because you folks collect measurements like porosity, quartz content, permeability, calcite content, and total organic carbon and things like that. And you have all of these different measurements, and you want to see which data points have similar characteristics or which data points belong to a group, and what are the differences between one group and the other. So can we group them in a separate fashion? And that's called unsupervised clustering. It's called unsupervised clustering because when I saw this data, I did not know how many clusters are going to be there. I did not know how many groups are going to be there. There is no output. There's only input that I have, and I'm trying to predict patterns in this data. I'm trying to find groupings within this data, and that's unsupervised clustering. And if you understand these 2 things, then pretty much that's all there is to most of machine learning that we do. And there are other more, the differences come about in the different kinds of tools or algorithms that we use in going about doing supervised learning or unsupervised learning. For those of you who've done regression, you can fit a straight line through a bunch of points. You can fit a quadratic equation. You can fit splines all of them within Microsoft Excel. There are 3 different methods by which you could fit the same data set. So that's what I mean in terms of the mathematical formulation being different. Okay, so why has this become such a big buzzword in the in petroleum engineering and geosciences? All of us are familiar with OnePetro. And if you go to OnePetro and then put a search for machine learning, you would essentially end up with thousands and thousands of papers, most of them published since about 2016. I think a large percentage, I forget the numbers, but a large percentage of them were published since about 2016. And so the question we're going to ask ourselves is, why? What happened in about 2015? What happened around 2016? And I think our previous speaker talked about that a little bit, but here's the thing. I'm just showing you one example of one single play. This is a map of Texas, and over here is the Gulf of Mexico. This is the Texas and Mexico border, and this line over here is the Rio Grande. And this set of lightly colored patches over here denotes the Eagleford Formation, one of the largest oil producing formations in the US, which was hardly producing any oil prior to 2005, 2006. And each dot over here represents one single well. And there are roughly about 20,000 dots in this picture. Each and every one of them drilled and completed in the last 10 to 15 years, 20,000 wells. Imagine that. So, and the question that operators are asking themselves is, where do I place the next well? What sort of well spacing should I be using? How should I complete my well? How many fracture stages do I need? How much of proppant and how much of fluid should I be pumping into these wells? How do I optimize my production and minimize cost? Everybody's concerned with that specific question. Now, there is no physical model that can give you an answer to that question. What you can do is you can look at historical performance across each one of these 20,000 wells and begin to start making sense about the relationship between well productivity and completion size and well productivity and formation properties and things like that, so that you can place your next well with a high probability of success. So this is just one snapshot, but you can imagine that each and every one of these wells is associated with different kinds of artificial lift. Each one is about 1 mile long or 2 miles long. They're connected to different kinds of instruments, and each one of them recording data minute by minute or second by second, and sometimes even more at a higher frequency. So we're collecting those vast amounts of data, and we want to make sense of it. Okay, so with that background, just one last slide before we jump into the applications. So this is my personal opinion. What you're looking at over here is something called the Gartner Hype Curve. They are a market research firm. And essentially what they do is they go and poll different kinds of technologies, and they see what are the expectations from that technology. Do we have second generation or third generation products and things like that? And so they typically plot things on a graph of expectations on the y-axis versus time on the x-axis. And typically most technologies, it doesn't matter which one you're looking at, typically go through this upswing in expectations in a very short period of time. Because think about driverless cars. When they came out in 2006, 2007, everybody was excited that we'd be having driverless cars by 2020. But turns out that we hardly have any driverless cars right now. Why? Because as with any technology, there is going to be some negative press. The driverless car went and crashed into some pedestrians, killed some people, crashed into a cyclist, destroyed a traffic light. So you begin to see that people start tempering their expectations. And then what happens is that you may have had 20 different companies that were developing driverless cars. They merge or they go out of business, and then you begin to start seeing second gen and third generation products. So the reason why I'm putting this graph up over here is because I think in the oil and gas industry, we are still in this region over here where there is quite a bit of hype and quite a bit of expectations from artificial intelligence and machine learning. We're not yet over here where we're mature, where it's a mature technology. Machine learning is quite mature in other fields, but in the oil and gas industry, it's not so mature. And I'll tell you why. The reason is because some of you would be drilling engineers, and you know that you provide your daily drilling report as a PDF document. Some of you are completion engineers who draw well diagrams in a PDF document. There are some of you who are production engineers who perhaps report daily production in an Excel spreadsheet. And different business units and different operating companies have different ways in which they report data. And so we don't have that unified collection and reporting and access to data. You as a drilling engineer, if you wanted access to some reservoir related data, perhaps that access isn't there, and that's shared throughout the industry. And until we fix that problem, we're not going to be getting to this point over here where we have mature technologies and we see the best, we see the benefits of the adoption of machine learning. Okay, with that background, we'll get started. I'm going to talk about two applications. Both of them are very, very similar. Both of them are going to be using surface drilling data. One of them is going to be looking at real-time geosteering, and the other one is going to be looking at optimizing hydraulic fracture locations along a horizontal lateral. And both of them are field case studies. This is not a toy example by any means. We've applied them to actual field case studies. So this is the first one. We're going to be looking ahead of the bit for real-time geosteering. And so let me give you the problem statement. So you're drilling from a location up over here. You have a 6-inch bit, and the 6-inch bit is roughly about 3 kilometers away. And it's making hole 3 kilometers away, horizontally 3 kilometers away. The depth might be about 10,000 feet. And so it's 3 kilometers away. And we know that when we're drilling a horizontal well, perhaps we're not perfectly horizontal. Our wells are going to be doing porpoising, something like this. So one, we want to use something that's readily available to say something about what the bit is doing. Where is the bit located? What kind of formation are we drilling through? And of course, we have solutions to that problem. We of course have MWD subs and we have LWD subs, but I want you to think about this problem. The bit is over here. The MWD sub or LWD sub might be about 120 feet behind the bit. So the bit is doing something and the MWD and LWD sub is reading something which is 120 feet behind. And so by the time the bit moves, by the time the sub comes to where the bit is currently located, you've gone another 120 feet and you've drilled some more formation. So the thing is, it's too late. So what can we do using real-time information that's available on the rig floor to say something about what the bit is doing? So you can imagine if the bit is cutting through rock, you can imagine that the mechanical properties of the rock are influencing rate of penetration. They're influencing the torque, and they're influencing RPM and things like that. And of course, weight on bit is going to be influencing rate of penetration and things like that. But we have all of these numbers which we're collecting in real time on the surface. So can we make sense about, can we say something about what the bit is doing, so that if the bit seems to be going out of zone, we can bring it back into zone. We can also say something about the different formations that the bit is penetrating. So that's the purpose of this analysis. And of course, as with most cases, we make some assumptions. The assumptions are that the bit, the data that we're reading is sensitive to bottom hole assembly changes, but most of the data that we analyzed, the BHA was quite similar. We also made sure that any influence of changes in the drilling crew was minimal. So we removed all of the crew changes that happen every 12 hours. And of course, you can't treat vertical and lateral sections together. You have to separate them out because your analysis in the vertical section is going to be different from your analysis in your lateral section. Okay, so having said that, I know this is supposed to be a broader presentation, but I'm just going to quickly tell you something about some of the methods that we chose. You are familiar with supervised learning. Turns out that this did not do a very good job, but something called the hidden Markov model and change point detection did a very, very good job. And I'll tell you what the hidden Markov model is. So if all of you had your cameras on, I could perhaps look at you and see what all of you are wearing. And even though I'm not sitting in Lima in Peru, I can say something about the weather outside, because some of you might be wearing jackets. Most of you might be wearing jackets, and that's an observation that I have access to. I don't have access to the weather report in Lima, but if all of you are wearing jackets, I can say that it's very cold outside. Dr. Amar Kanchi is wearing a jacket, so I suspect that it's cold outside. So Dr. Amar Kanchi is my observation. The state of the system is the weather outside, which I can't observe. That's exactly what we have over here. We have the natural world has processes that has some outputs. In our specific case, we're recording some observations on the rig floor, things like RPM and torque and weight on bit and rate of penetration, but we don't know what lithology we have at the bit. So can I take this drilling data and say something about this state of the system? So when we talk about hidden Markov models, we talk about state reconstruction. That's the mathematical formulation. And so that's one of the models that we used. The other one is very, very simple. And it's called change point detection. To illustrate the change point detection, look at the graph on the right-hand side. I have temperature on the y-axis versus time on the x-axis, and you have the actual data shown in blue, and it's quite noisy. But if you were to eyeball this data set, you can sort of say that over here, it's one level, then somewhere around 1910, things changed, and then it's another level, then around 1920, things changed again, and then there's another plateau over here, and so on and so forth. And you can see that every time you have this big discontinuous jump, we call them as change points. And so change point detection, this is temperature versus time, but you can imagine that when we're recording drilling data, this might be something like RPM versus time, or it might be RPM versus depth. It can be torque versus depth. It can be rate of penetration versus depth, or rate of penetration versus time. Doesn't matter. I have multiple signals, and I'm going to identify change points on those multiple signals. And the hope is that when you have these changes over here, these changes are occurring because of something happening in the subsurface. That's typically a change in lithology, or it's happening because of something on the surface that could be a crew change. We know when crew changes occur, we can remove change points because of crew changes, and we can only retain what's due to some subsurface phenomena. Okay, and then of course, there's the unsupervised and supervised learning workflow, where you have a bunch of measurements, and you can essentially come up with different kinds of groups, and you can populate the entire lateral of the well with these different groups. I have rock type 4, 3, 2, and 1, and I can populate all of these things. The question we're asking ourselves is to be able to use drilling data, things like ROP and weight on bit, to predict these different rock types that I have over here. I use things like gamma ray and bulk density to populate these rock types, but can I use drilling data? Is drilling data sensitive to this? And you can use a whole host of algorithms. Some of you may be familiar with the names like support vector machines or random forests. You can do things like that. So just to illustrate the point, so here you can have ROP on the y-axis, weight on bit on the x-axis. And I already know the clusters in a well that has drilling data and well log data, because I used well log data to construct these clusters. And I have rock type 1, I have rock type 2, I have rock type 3, and I have rock type 4. So if I go to a new well and I'm recording ROP and weight on bit, and the new data point lies over here, then I know that I'm drilling through rock type 4. If it lies over here, I know that it's drilling through rock type 2. And essentially, you just have to come up with these decision boundaries that distinguish between the different data sets. This is your supervised learning over here. Anyway, so that's what we did. So let's see, we have applied this to a couple of unconventional fields, but I'll show you a very nice example, which is a publicly available data set, which is actually from the North Sea, just offshore Norway. It's a real field with about 15 wells, produced about 63 million barrels. And for those of you who are interested, you can go and look at this data set. It's available publicly. So what did we have in terms of data? We had triple combo data and sonic data. And we can use all of this triple combo data to construct rock types as a function of depth. So depth going from 3,500 feet to about 3,700 feet. You can see gamma ray, sonic travel time, and bulk density. So this is all very fine, because once you record a log, you know what your rock types are. But my question or thing we're attempting to answer is drilling data sensitive to these changes in rock types? And so we're going to be using those 3 different methods. And first, I'll show you the results from change point detection. Here I'm plotting mechanical specific energy versus depth, ROP versus depth, weight on bit versus depth, torque versus depth. And I have these 4 different, these are drilling variables. And I have these vertical red lines. This is what my change point algorithm detects as a change point. Something substantially different happened at this location. Something substantially different happened at this location and this location and this location, and so on and so forth. And so if you look at this drilling data, perhaps you can say that this is a false change point. This might be a true change point, because you can see there's a huge change in the signature on weight on bit. There's a change in the signature on ROP as well as mechanical specific energy. And then same thing over here. These 2 change points bound a huge change in the operation, drilling operations. Let's see if these change points correspond to changes in lithology, because that's what we're asking for, right? So here, I'm going to plot that same graph in the back, but I'm going to color the data points by the different rock types. You can see that this is obviously a false change point. No machine learning algorithm is perfect. But then as I'm drilling along, I get a change point over here, and you can see that that's because of a change in lithology. I went from rock type 1 or 3 to rock type 2. And then I'm drilling along rock type 2, and then I detect another change point. And that change point represents a transition lithologies, a false change point over here, a false change point over here. But this denotes a change in lithology, And you can see that change point detection does fantastic. And this is great because now I can be recording these variables in real time and tell you whether you're drilling through rock type 1 or rock type 2 or rock type 3, and give you that information. Does it work with hidden Markov models? Yes, it does. So if you plot all of the variables, ROP, MSE, bit weight, and torque, and pressure, and things like that, and see what the hidden Markov model predicts as the different states, because hidden Markov models works with the concept of states, you can see that this is state 3. The black dots are state 1 and the red dots are state 2. And you can see that just ROP versus MSE, there's a separation between the 3 different states. And it turns out that these 3 different states actually correspond to different lithologies. So over here, I'm plotting gamma ray versus depth on the x-axis, and I'm showing you the different rock types. And I'm plotting the same data, gamma ray versus depth on the x-axis, but in terms of the states. And you can see that whenever there's a change in lithology, there's a change in state. Whenever there's a change in lithology, there's a change in state. And so the thing is that even this hidden Markov model approach worked reasonably well in predicting changes in lithology from surface drilling data. It did not work so well in the supervised learning approach because we had quite a bit of striation, but it's something we can fix, but we didn't spend too much of time attempting to fix that. Not that the classical approach of unsupervised supervised learning is a bad thing. But having said that, what you can see is that surface drilling data, even though it's more than 20,000 or 30,000 feet away, you can use that to say something about the formation. So you can use it for real-time geosteering applications. And since you would be able to predict the rock types, you can say something about the mechanical properties of the rock types. So you can also begin to start predicting fracture locations in real time, because if you want to place fractures, you want to place them in locations where the rock is brittle, where you can have extremely long hydraulic fractures. so that you can connect to very, very large volumes of the reservoir. You can also predict problem zones, things that would cause lost circulation, things that would cause stuck pipe and things like that, because you can learn from historical data. And you can also learn from historical data to optimize your bottom hole assembly. So having said that, we're going to be looking at the next application, which is predicting fracture locations in real time using surface drilling data. And in this specific case, we actually used, I'll be showing you an example from the Marcellus Shale. And so the question you're going to be asking me is, why do I care about where I place my hydraulic fracture? So it turns out that if you go to any one of the fracking companies, what they're going to do is, if you have 2 miles of lateral, they're going to place 60 frac stages, and each one of them is going to be equally spaced. And so if they're going to be equally spaced, the question you're asking yourself is that optimal? Are we placing the fractures in the right spot? Should the fractures be in a location where the rock is brittle, where you have extensive natural fracturing, so you can create complex fractures and connect to a very, very large reservoir volume? So you'd rather have fractures that are not placed equidistant or equally spaced. So you can do that almost in real time using surface drilling data, because if you're going to be doing this after you've drilled your well and put your fractures in place, it's too late. You've already spent quite a bit of money to place your fractures. So this is the study area. It's the Marcellus Shale, which spans New York, Pennsylvania, and West Virginia. And it's, again, an open source data set. They have 4 wells in that specific location. And we had a bunch of data available for our analysis. So I'll walk you through the workflow and why specifically we're interested in the growth of fractures. So typically in this specific case, the well 3 had about 30 hydraulic fracture stages, and you can see the gas production from each one of the stages, which are quite different from one another. So the question is, why are these gas production rates quite different? Well, it turns out that maybe the locations aren't optimized. The second thing that we're interested in is, how does a parent well, the well that was drilled first, compare to the performance of your infill wells? So what typically happens is that when you frack your parent well, or when you frack your infill wells, the fractures are going to grow towards your parent well. And what's going to happen is you get something called a frac hit. If you get a frac hit, then this is your parent well production, and then you would get a decrease in production over here. And same thing happens with our child wells as well. This is what the parent well is doing, but your child wells are never as good as your parent well. So the thing is, the question becomes, what should be our well spacing be? Where should we be placing our fractures? And how long should our fractures be? Those are the kinds of questions you want to be asking yourself. So just a little bit more background. So it turns out that, yeah, we do have quite a bit of differences in production associated with each one of the stages. And the reason is because if you look at the fracture height shown in green and the length shown in blue, they are different for each one of the stages. Why are they different? Well, it turns out that every time we create hydraulic fractures, we are creating sound in the subsurface. We are creating little, very, very tiny earthquakes, just sound. And if you record the location, if you record that sound, you can triangulate and say where that sound originated from, or where did the rock crack. So let's look at the location of the sound for stage 10, which over here I'm plotting distance versus time on the x-axis. And these are all the dots that were collected. These are all the locations of cracking of the fracture that I'm listening to and placing in 3-dimensional space and recording as a function of time. And that's stage 10. Stage 10 has, again, using what do you call it? A micro resistivity log. You can begin to also know how many natural fractures I have. An imaging tool, you can say how many natural fractures you have over here. And in this specific stage, there were only 14 natural fractures, again using an imaging tool. And let's see what's the pattern of behavior of the microseismic dots when you plot distance versus time for stage 14. So stage 14, again, we can see this collection of these different dots occurring at different times, at different distances from the location of the perforations. And what you can also see is this line that I'm drawing over here. This is a square root time line, and you can see that it bounds each and every one of these dots over here. So all the dots show a square root time dependency, but here it's more scattered, more random. So why is that happening? This is happening over here because I have more natural fractures. So if I'm pumping fluid through perforations, the fluids are going to go through the perforations, connect with the natural fractures, and go out everywhere and form a very, very broad swarm of fractures. On the other hand, when I don't have too many natural fractures, what's going to happen? When I pump fluid through the fracture, through the perforation, it's going to create a nice long planar fracture because it has nowhere else to go. And this is a classical signature of a planar fracture. This is a classical signature of something that's more complex. Okay, good. So we're seeing differences in length and differences in width that can be attributed to the fact that you have different natural fracture counts. So what did we do? We went back and looked at data from this well over here, which is MIP3H. And we were able to extract the well logs from this specific well. And we were able to identify 3 different rock types. So the rock types are rock type 1, 2, and 3. And I'm showing you the Young's modulus for each one of those 3 different rock types in well 3. You're looking at the Poisson's ratio for each one of those 3 different rock types. You're also looking at the brittleness index for each one of those rock types. In general, a rule of thumb is a rock is more brittle if you generally have a low Poisson's ratio and generally a relatively high Young's modulus. So in general, just looking at this whole data set out over here and the brittleness index as well, you can see that the brittleness index for rock type 3 is somewhat higher than that for rock type 1 and rock type 2. And so if you were to place fractures in well 3, you would be looking for locations which have a preponderance of rock type 3. So good. So we went through that same unsupervised and supervised learning workflow. I know the distribution of rock types along my wellbore. The question is drilling data sensitive to these different rock types with different mechanical properties? It turns out that it is. So without going into the mathematics of the whole thing, in well 3, we actually know what are the distribution of the rock types. You can see the red colored rock type, the blue colored one, you can see the black colored one, and you can also see the red colored one. So we have 3 or 4 different rock types. And then we use different machine learning algorithms to take drilling data and predict the distribution of those rock types. And you can see that this is one of the methods. You can see that it's a very, very close correspondence to the actual rock type distribution. It's doing quite well. Another algorithm is also doing reasonably well. Another one's also doing reasonably well if you compare it to the true value. And there's finally another method that we tried, which didn't do as well. And this is actually a neural network, which didn't do as well. Perhaps we could have changed the neural network architecture and improved our predictions. But the point I'm trying to make over here is that when we talk about machine learning, irrespective of the application, there is no one size fits all. You have to try different methods. What might be a KNN, K nearest neighbor, will work really well over here, but may not work in another application. But having said that, you can see that drilling data is sensitive to the distribution of rock types, and we were able to successfully show that. We were also able to look at the importance of some of the features that we used in prediction. So you're looking at gamma ray at the bit, you're looking at mechanical specific energy, and you're looking at mud gain and loss as some of the more important variables. And this is very, very important. Yes, you can get accuracies, but the question becomes, can you predict can you tell me which is the most important variable? Because you want to be spending money on getting more data related to that variable. And you can see that when you're talking about predicting mechanical properties, mud gain and loss is actually a very, very important variable. And if you think about it, it is going to be important because zones that are highly fractured, which have quite a bit of natural fractures, are going to experience quite a bit of mud loss. And those are the zones that are probably more brittle. And so in predicting different rock types, this is one of the variables that is actually quite important. So you can go back and do that kind of analysis. In any case, just since I'm almost out of time, I just want to mention that there are several different applications associated with machine learning. In this specific talk, I was showing you about drilling data, and how you can characterize your reservoir. And typically you would use these things where physics-driven models do not exist. You don't have any physical model that can take surface drilling data and tell you something about the properties of the rock. And so having said that, this talk was about subsurface applications of machine learning. Other things that several people as well as I are working on are related to distributed temperature sensing and acoustic sensing, reservoir characterization. I believe the next talk will be related to the geosciences. So there's quite a bit of work going in the geosciences. There's also quite a bit of work going with synthetic log generation because we don't record sonic, for instance, every time. So you can predict sonic. You can also do decline curve analysis. And here's a nice example of some of the things that some people are doing and we're doing as well, is looking at dyno cards from pumps and seeing whether the specific the pump is operating normally or whether there's excessive vibration or whether there's sand in the pump or there's some gas leakage or gas emerging or things like that. So you can begin to look at dyno cards and begin to start predicting what kind of failure you have. And again, that all is predicated on having a very, very large data set. So to end my talk, machine learning is really, really promising. There are multiple extremely nice applications over there. One of the problems that I mentioned when I talked to you about the Gartner hype curve is the fact that data warehousing and reporting are still roadblocks for us because we don't have industry standards. We don't even have company-wide standards. If you think about it, each company does things differently. Within a company, different departments do things differently, drilling versus production versus completions, and different groups don't have access to the data. So the thing is, that's one of the biggest challenges that we're facing right now. It's not the algorithms, it's not the mathematics, it's this that is really a challenge right now. The other challenge I would I think is very important is the fact that we don't have enough petroleum engineers and geoscientists trained in machine learning. And so if you are interested in since I'm perhaps speaking to a whole bunch of students over here, I would highly recommend that you folks take courses related to machine learning so that you folks, when you go out to the industry, you become more marketable and you can start to make sense of all of this vast amount. Hola. So that's largely what I wanted to share with you. And thank you very much for your patience and for spending your afternoon/morning with me.
Thank you. Muchas gracias, Dr. Deepak. Muchas gracias.
Thank you.
Thank you. Indeed, so it opens a window of great opportunities. The few examples that are very with tangible outcome, the jobs that you have done. Let me convey the message to the audience. Definitivamente muchas oportunidades con el tema de aplicaciones en subsurface de machine learning. Entonces, abrimos las preguntas. So let's open the questions. Mr. Franco Casinelli. Yeah, Mr. Franco Casinelli mentions, is it important in machine learning well oil applications to process the data in situ close to the well, or it is better to do it in a server, on a server? What operational advantage has each of these implementation options?
So I think that's a very, very good question, and it depends on the infrastructure available. So one of the things that we are seeing increasing adoption of these days is real-time transmission of data from the well site directly to a control room at the company's headquarters. That's something that we're seeing, whether it be drilling data, whether it be completion data, whether it be pump data. So you could be having several different ESPs and pump jacks, which are actually streaming data to a central control room. And it is so to answer your question, Franco, it depends on the application. If you're going to be doing something related to reservoir characterization, it's perhaps not very time sensitive. Something like if you can provide a solution within a couple of days or maybe a couple of weeks, that would be a reasonable time frame. But if you're talking about predicting failure, or if you suspect that there is failure, you want the solution almost immediately. And so the thing is, having that access to real-time data becomes really very important, especially when you're talking about pump data, when you're talking about drilling data, because a driller would, of course, know based on his or her experience in the field that probably we're going to be going to a zone that has experienced stuck pipe in the past or lost circulation. But if it's a new person who's got no experience in that field, or if you folks go out and drill in someplace else, then you don't have that experience. And that's where machine learning in real time, or interpreting data in real time, becomes very, very important.
Great, thanks. A question from Francisco Porturas. What are the main pitfalls in machine learning interpretations that you have come across?
So that's a very, very good question. I would love to spend quite a bit of time talking about this. But one of the really nice websites that I like is actually called Spurious Correlations. Let's see. This one over here. It's called Spurious Correlations, and I hope all of you can see this specific website over here. So I'm going to show you one of my favorites. So let's look at this picture over here. You're looking at per capita consumption of mozzarella cheese on the y-axis. You're looking at number of PhDs in civil engineering versus number of PhDs in civil engineering versus time. And so this is real data, and you can actually see it's a very nice 1:1 correlation. The more cheese you consume, the more PhDs you have in civil engineering. So this is, and that's why, to my last point in my presentation, I think we need more oil and gas people or petroleum engineers and geoscientists learning about machine learning so that we don't make these kinds of mistakes, because we understand the problem. We are subject matter experts. We are not going to be making mistakes like this. And so that's one of the biggest challenges that we face as an industry. But there are several other challenges to your question, to machine learning. We always think that the fanciest part of machine learning is just hitting the run button on some piece of code or some piece of software. And that is, it's very nice. Some of the vendors that are coming out with things these days come up with very nice plotting schemes and things like that. But you can actually do lots of things on your own. And when you do things on your own, you will find that you are spending roughly about 80 to 90% of your time just collecting the data, putting it together, removing the bad data, and making sure that the data set is ready for the application that you're looking for. And that will take you 80 to 90% of your time. If I were spending, or if my student were spending, say, about 4 months working on a specific problem, I guarantee you that my student was spending roughly about 3 to 3.5 months gathering that data, putting it together, tabulating it in some fashion, before that student wrote the code and hit the run button. Hitting the run button, at the most, maybe a day or 2 or 3 days. Maybe you do it 5 or 6 times just to optimize it. So maybe at the most 2 to 3 weeks, but you're spending 3 months collecting the data and cleaning up that data. And that's one of the biggest challenges.
Wonderful, wonderful, very nice, well explained. Thank you. So guys, the message 80-90% is preparing the data. Yeah, and finally, we have many questions, but we have more than 100 people with us, and also Facebook. Definitely, we cannot answer all of that because we have also Dr. Susan Nash. Very interesting presentation. Last question: have you come across a project regarding the natural gas projects or applications?
So yes, I mean, when you're talking about natural gas projects, there's been quite a few. So when we talk about natural gas, there have been quite a few applications on the downstream side of the business. Because if you're talking about pipelines and you're talking about compressor stations and things like that, when you're talking about the health of the facilities, people have devoted quite a bit of time on surface facilities as well as refineries to get all of this sensor data and then begin to start learning or training a machine learning algorithm to recognize normal operation versus maybe some abnormal mode of operation. It might be stuck pipe, it might not stuck, it might be a blockage in the pipe, it might be a leak in the pipe and things like that. So there have been several different applications associated with the surface facilities in the natural gas area, as well as in the refineries and any other equipment. Subsurface applications related to natural gas, quite a few, but nothing different from what's going on with oil-related applications. So if you're asking about something that's different with respect to natural gas, nothing really. I mean, whatever you do for, say, pumps, that same algorithm, that same workflow can be applied to compressors. The only thing is that the measurements are going to be different. The failure modes are going to be different. But essentially, whether you're doing predictive analytics on a pump, a downhole pump, or a surface compressor, or a pipeline, or an entire distillation tower, it's pretty much the same workflow.
Thank you, thank you. And finally, something interesting for us, we have a team, EOR team. Any application on EOR that you can quick mention?
I'm not aware of applications related to EOR, Dr. Samarkanchi. Yeah, because one of the problems with EOR projects, I mean, so if you're going to be doing any kind of machine learning, one is we need lots and lots of data. So we need lots and lots of data of the same kind of project. So if you were attempting to do something related to miscible floods, for instance, then maybe if you were able to collect a whole bunch of petrophysical properties and fluid properties and solvent properties and wettabilities and things like that, maybe you could begin to start saying something about what sort of solvent may be applicable in a specific field or things like that. But it's really, really hard to come across that data, very hard to come across those kinds of applications.
The label, exactly. The label data, thanks. Yeah, we will have something in the afternoon. I hope we can share that with you, but that's definitely, you are right, pointing the labeling of the data is a big problem. Thanks. Let me share with, let's have un aplauso virtual. We say we are going to virtually congratulate you for your great presentation, Doctor. Many, many thanks. Thanks a lot for your presentation and further success with your great interesting projects.
Thank you very much. Appreciate it.
So